Hi everyone. I'm going to talk about a joint work with my advisor Moses on explainable clustering. So our work is motivated by a recent research trend on the explainability of machine learning models. So usually machine learning models have several characteristics that we like. So these models are learned from data, so they are not designed explicitly by people. In some sense, machine learning is a way to automate algorithm design, so we can learn these algorithms from the data rather than designing them explicitly ourselves. And also, these models tend to be very powerful, and they can be used in a lot of applications. And a lot of the applications we use machine learning models involve people. So for example, loan approval and medical diagnosis. So these characteristics are good, but they sometimes also cause problems in practice when we deploy machine learning models. So specifically, since these models are not designed explicitly by people, so it's quite possible that no one really understands the model. But on the other hand, since we want to use this model on people, so we need to make sure that these people trust the machine learning model. So this motivates explainability, which requires the machine learning model to not only output just predictions and decisions about individuals, it also requires the model to output explanations for these predictions and the decisions. And the hope is that by providing explanations, this helps build people's trust in these machine learning models. So this is the general background about explainability. And in this talk, I'm going to focus on a particular type of machine learning model, which is clustering. So the basic setup is we have data points in a Euclidean space. And what the clustering does is that it partitions these data points into a number of clusters. And the hope is that the data points that are clustered into the same cluster have similar behaviors. So this tells us some structure about the data set. This is the basic setup. And usually we can measure the quality of a clustering by using certain cost functions. So for example, a very popular cost function is the k-means cost function. So to define the k-means cost function, we locate a centroid for each cluster, and we look at the distance from each data point to its assigned centroid. So specifically, we take each data point, we compute its L2 distance to its assigned centroid, and we take the square of that distance, and we take the sum over all of the data points. So that gives us the k-means cost. And in this talk, I'm also going to talk about several other cost functions. For example, the LP k-means cost function. So here, instead of using the L2 norm to measure the distance, now we use LP norm. So this is a more general cost function. So if you take p equals 2, then this becomes the usual k-means cost function. And also, I'm going to talk about the LP k-median cost. So here, we no longer take square of these distances, we just sum up these distances themselves. Okay, so these cost functions can tell us the quality of a clustering. Obviously, if the cost function is small, then the clustering is good. If the cost function is large, then the clustering is bad. And it also tells us how to find a good clustering. So to do that, we just need to locate centroids so that we minimize a certain cost function or approximately minimize a cost function. And then the clustering is given simply by taking each data point to its closest centroid. Okay. So this sounds like a very simple framework. We have a cost function, we locate centroids, and we minimize the function to get the clustering. So it seems that the explainability shouldn't be an issue in such a simple setting, but it turns out that explaining clustering can be quite challenging. So suppose I take a data point in the data set, and we would like to explain why this data point belongs to this cluster. And you may say that, oh, okay, so the reason that this data point belongs to this cluster is because it is closest to this particular centroid. But then you also need to explain how you computed these centroids, and also even how to compute distances between data points. So these things are not at all obvious, and also we want the explanation to also work for the general public, on which the clustering model is used on. So essentially we want to build a clustering that is more explainable, and this motivates this recent notion called explainable clustering, which was proposed by Dasgupta, Frost, Moshkowitz, and Rushton. So here we have three figures from their papers. On the left figure, we have usual k-means clustering. So here k equals 5, so we have 5 clusters. And in the middle figure, we also have 5 clusters, but now we have an explainable clustering, which is the new notion these authors are proposing. So if you look at, if you compare these two figures and see what's the difference, so there are two major differences. So first, the clustering boundaries in the second figure are all axis parallel, and also the clustering in the middle figure can be constructed using a decision tree shown in the figure on the right. So these two requirements, namely having axis parallel boundaries and having the clustering be determined by a decision tree, these two requirements are called the explainability constraint. And explainable clustering is simply clustering under this explainability constraint. And since this is a relatively new notion, and there are a lot of questions people are trying to understand about this notion, and one particular question that people are very interested in is how much does this explainability constraint increase the clustering cost? So here by costs, I mean just LP k-means cost or LP k-median cost, which I defined earlier. And people study this notion called the price of explainability, which is defined to be the optimal cost under the explainability constraint divided by the optimal cost without the explainability constraint. So in this figure, it's just the cost in figure B divided by the cost in figure A. So since the introduction of this notion of explainable clustering, multiple research groups worked on this problem, and they tried to prove bounds on the price of explainability. And in the original paper by Dasgupta, Frost, Moshkowitz, and Rushton that proposed the notion of explainable clustering, they already showed some upper and lower bounds on the price of explainability in different settings. So specifically, they showed this for L1 k-median and for k-means. And of course, if you compare the upper bound and the lower bound, you see large gaps in these bounds. And also, from this, it seems that the upper bound for k-means is much larger than the upper bound for L1 k-median. And then after this work, a lot of research groups worked on improving these bounds, and these improvements come from papers that are independent to our work. And these independent work improved the bounds on the price of explainability for both L1 k-median and for k-means. And now you see that the upper and lower bounds almost match each other. So this is great progress in this problem. And our work is motivated by the observation that the bounds for k-means seems to be much larger than the bound for L1 k-median. And this seems bad. This tells us that we need to pay a lot in the clustering cost by having the explainability constraint. So our motivation is in what settings can we improve the bound for k-means? And also, if we go back to the figures we just saw, if we compare the clustering in the left figure and the clustering in the middle figure, we don't see much difference in the clustering. It looks roughly the same, and only a few points changed their cluster, their assigned cluster. So you should expect that the price for explainability should be rather low in this figure. So why is it that in the theoretical bounds, the price for explainability seems to be super large especially for k-means? And one reason for this is because that these figures are drawn in two dimensions, and all of these theoretical bounds, they need to hold for every dimension, even when the dimension is infinite. So we ask this question, which is whether we can achieve better upper bounds that are dependent on the dimension d, and when the dimension is d, and when the dimension d is small, can we get better bounds for the price of explainability? So before our work, there is already results about the price of explainability that are dependent on the dimension. So specifically, Isfandiari, Murakami, and Narayana already showed dimension-dependent bounds for L1K medium. And so as you can see clearly now, the upper and lower bounds that depend on the dimension d. And also when the dimension d is small, then the bounds are also small. So this is great. And in our work, we show dimension-dependent bounds for k-means. So we show that essentially the price of explainability for k-means grows roughly like as a function of k to the 1 minus 2 over d for both the upper and lower bound. So an interesting special case of our result is when the dimension d is 2. So in this case, k to the 1 minus 2 over d is just a constant. So in this case, we show that the upper bound can be as small as log k log k. And before our work, even for 2 dimensions, the best result was order k log k. So we achieve quite a significant improvement in this setting. Okay, so next I'm going to talk about the techniques we use to achieve these results. And before that, I would like to pause for a few seconds to see if you have questions about the result statements.
Do you have mentioned a lower bound for d equal to 2? Do you know whether it's log k log k or something smaller than that?
I'm not sure I hear you very clearly. Are you asking about the lower bound for d equals to 2?
That's correct, yes.
Yeah, so good question. So essentially, I think the best lower bound I know for d being 2 for k-means is some constant larger than 1, I suppose. If you look at the lower bound here, if you plug in d equal to 2, then this makes no sense because this is some quantity that is smaller than 1. So yeah, this lower bound becomes vacuous if d is 2. But I think for d being 2, the best lower bound I know is some constant larger than 1, and I think it's I believe is still an open question to improve the upper bound to match the constant lower bound. Yeah, does that answer your question?
Yeah, sorry, I have another quick question. So how should I think of k versus d? Are they just completely 2 different parameters, or for the purpose of this talk, should I think of k as being much larger than d, or d as being much larger than k, or yeah?
Yeah, good. Yeah, that's a good question. That's a good question. Yeah, I think if you, I'm not sure if I have a very good answer to your question. But if you compare our bounds and the previous bound, you'll see that essentially the improvement in our bound comes in a case where the dimension d is smaller than log k. And in some sense, like for this problem, I feel that the dimension, the log k is in some sense like a threshold for the dimension. Like if the dimension is smaller than log k, then some like you can get some improvements because of the low dimensionality. And if the dimension d is larger than log k, then you don't get like improvement based on the dimension. I think, and I think that also holds for k median. Like if you look at the upper bound for L1 k median, you'll see that since it's a minimum of two things, and if you set these two things to be equal, then you will see that d is roughly log k. So it seems that d being log k is like the threshold. For this.
Sorry, just as a follow-up. So there's one thing about where it improves upon the previous result, but is the setting where d is much larger than k still meaningful? I mean, even if the prior result already gives a nice guarantee, is it still interesting to think of d being larger than k? Because these are things that are interesting, for example, for mixtures of Gaussians. But I was wondering if something.
Good question. Yeah. That's definitely an interesting setting. That's of course, and however, for d being larger than k, like if you look at lower bound, then essentially it's showing that you don't get much improvement by like knowing the dimension, like specific in this setting. Like you would even though like in the case where d is larger than k, it's roughly the same as d being infinite, like in this problem.
Thank you.
Okay. So now I'm going to talk about the techniques we use to achieve our results in a k-means setting. And I mainly focus on 2 dimensions because like it's easy to illustrate. It's easy to draw pictures in 2 dimensions. And also in 2 dimensions, we achieve the greatest improvement compared to previous result. Yes, and another reason for focusing on 2 dimensions is because in 2 dimensions, all different kinds of norms are the same. Like all different kinds of norms are bounded by up to constant factor by each other. So here I mean like LP norm for all P. So you shouldn't be surprised if I'm using the L infinity norm all over the place, although our results are in the standard L2 norm. Okay. So at a high level, our algorithm is a recursive post-processing algorithm. So what does this mean? So essentially, I would say that all of the algorithms, or I guess most of the algorithms used in these recent papers on explainable clustering uses recursive post-processing algorithm. And so first of all, our algorithm is a post-processing algorithm, so which means that the algorithm starts from a solution without the explainable constraint. So it starts from a usual k-means solution like this. And then the algorithm tries to modify the solution so that in the end we get an explainable solution. That's why it's called post-processing. So for example, since explainability requires us to have x as parallel boundaries, so we could try to enforce this vertical line to be to be a boundary, to be a clustering boundary, then you will see that we need to make some modifications, right? For example, for this point x, it was initially assigned to this centroid A. And now since we want to enforce this vertical line to be x boundary, we need to reassign x to the centroid B. So after we do all of these modifications, the problem divides into 2 sub-problems, one on the left and one on the right. And we just solve these 2 sub-problems recursively. So here for the sub-problem on the left, it only has one single cluster, so we don't need to do anything else. But for the sub-problem on the right, we still have 2 clusters and we want to separate them. So we use this horizontal line. And finally, we get an explainable clustering because now the clustering is determined by a decision tree and it also has access parallel boundaries. Okay, so this is the general framework of the algorithm. And the goal of the algorithm is, of course, to choose these vertical lines and horizontal lines so that we can minimize the reassignment cost induced by these reassignments. So to do that, our ideas come from inspirations from several previous papers. So one of the previous papers that inspired our result is a paper by Dasgupta, Frost, Moshkovitz, and Roshen. So this is the original paper that proposed the notion of explainable clustering. So in their paper, they showed bounds on the explainability, bounds on the price of explainability for L1K median. And here I'd like to translate the result from L1 norm to L infinity norm just for the purpose of illustration. Seems that L infinity norm is easier to explain, but it also uses essentially the same idea. So let's look at what they did in their paper. So since we use a recursive post-processing algorithm, so let's focus on a single cut that divides the problem into two sub-problems, one on the left and one on the right. And let's try to bound the reassignment cost induced by the single cut. And then finally, we just add up all of such cuts and add the reassignment cost over all of the cuts, and that would give us a bound. Okay. So let's focus on the single cut. So this cut cuts through two data points from their centroid. So we need to reassign these data points. And we would like to bound the reassignment cost. And we use a very simple triangle inequality to do this. So the reassignment cost of a point, which is defined to be the new cost minus the old cost, is obviously upper bounded by the diameter, which is defined to be the maximum L infinity distance between two centroids. It's just because of triangle inequality. You move from one centroid to another centroid, so that the cost you pay is upper bounded by the distance between these two centroids. And since we are using the L infinity norm, the diameter can be defined in a slightly different way. So we take a rectangle with a smallest rectangle containing all of the centroids, and the diameter is defined to be the maximum side length of that rectangle. Okay. So this gives us a bound on a very easy bound on the reassignment cost. So whenever we see a point being reassigned, we just say it pays an additional diameter. So that's the reassignment cost. And of course, then since a single cut can cut through multiple points, so the total reassignment cost is just the number of points reassigned times the diameter. So this gives us an upper bound. And you might think that this is a very loose upper bound, but it turns out to be quite useful. So let's continue. So we assume without loss of generality that W1 is larger than W2. This doesn't matter. You can just label them however you want. And since the diameter W is defined to be the maximum of W1 and W2, so in this case, the diameter is just W1. And now we fix a point X and its current centroid, and we project them down to the direction of W1. So now we would like to define a function for this pair, for this point X and its centroid. So this is a piecewise linear function. So it has three parts: the left part, middle part, and right part. The left part of the function is the constant zero function. So this is not very interesting. And the right part of the function is also a constant function, but it takes the value Lx. So Lx is defined to be the L infinity distance from X to its current centroid. So this is just the contribution of X to the L infinity K median cost. And the middle part of the function just connects these two, the left part and the right part, using like a straight line. So this defines the function. And one interesting property of this function is that the gradient of this function in the middle part is lower bounded by 1. The reason is because the Lx is the L infinity distance from x to its current centroid, which is always lower bounded by the distance from x to its centroid after projecting down to the direction of W1. So that's why the gradient of this function in the middle part is always lower bounded by 1. Okay. So now we define such a function for each point x. So we projected them down and we draw this 3 parts function, piecewise linear function that is always non-decreasing. So for each point we have a such function, and now we take a sum over all of the points. So obviously the sum is still monotone, so it's non-decreasing. And the minimum value of that function is 0, and the maximum value of that function is the sum over all of the Lx. And now the interesting thing is that if we choose a value theta between 0 and w, so between the left boundary and the right boundary, and make a cut at theta, then the gradient of the function at theta is always lower bounded by the number of points reassigned by this cut. So the reason is because every reassigned point contributes at least 1 to the gradient. And since this function is a sum over all of the data points, so each reassigned point contributes to 1 to the gradient. So the total gradient must be larger than the number of points reassigned. Okay, so now we are ready to choose our theta between 0 and w so that we can control the reassignment cost. So let's start. So the total reassignment cost by this induced by this single cut is upper bounded by the number of points reassigned times the diameter. So this is the inequality I just mentioned earlier. And now since we also know the number of points reassigned is upper bounded by the gradient of the function at theta, so now we can bound the total reassignment cost by the gradient at theta times the diameter. So the diameter is w. Now we just need to locate a point theta between 0 and w so that its gradient is small, because like the diameter is fixed, we can't change that, but we can change the gradient at theta. So we can move theta from 0 to w and see where the gradient is smallest. And by the mean value theorem, there always exists a point theta between 0 and w so that its gradient is upper bounded by m divided by w. So this is simply because the function grows from 0 to m in the interval from 0 to w. So this by the mean value theorem, there exists such a point with small gradient. And we just take that point. And this bounds the total reassignment cost by m. So what is m? M is just the sum of Lx, which is exactly the infinity k median cost of this instance. Okay. Now, this bounds the total reassignment cost of a single cut. And since our algorithm is the recursive one, we can do this recursively. So we start from the initial instance, which is just a k-median solution. And then we make a cut. It divides into 2 subproblems, one on the left and one on the right. And we know that the reassignment cost induced by this cut is upper bounded by m. Okay, this is what we showed. And we can do this recursively. And then we know that the reassignment cost at each level of this recursion tree is upper bounded by m. And m is defined by the sum of Lx, which is exactly the L infinity k median cost of the original instance. And also we know that the depth of the tree is at most order k, because there are k leaves of the tree. And this implies that we just sum up the reassignment cost over all of the levels of the tree. So at each level we have m, so we have k levels. So this is the total reassignment cost is upper bounded by k times m. So this gives us a bound on the price of explainability, which is order k. Okay. So yeah, I'm going to pause again and see if you have questions about this analysis for k-median. Okay, sounds good. So, so this gives us some bound on the price of explainability for L infinity K median, but this bound is not optimal. So let's try to improve it. And the idea to improve the bound comes from this paper by Leiber and Martinho. So they gave improved bounds on the price and explainability for L1 K median. And again, I'm translating their results from L1 norm to L infinity norm. So what we just use is the mean value theorem. So if we have a function that that maps the interval from 0 to w to the interval from 0 to m, then we can find a point in that interval with this gradient bounded. So this is what we used. And the idea the idea that leads to an improvement is to realize that this mean value theorem can be improved in some sense. So here we can find a point theta in the interval so that the gradient times the diameter w is upper bounded by the minimum of f of theta and m minus f of theta. And of course, this is not exactly correct. And that's why I'm using this approximate less than equal sign here. And I'm going to ignore the precise meaning of this sign in this talk. And so why would this be useful? So so if we go back a bit and look at what we did. So essentially what we did is that the price of explainability is upper bounded by the depth of the tree. And since there are k leaves, then we know that its depth is at most order k. But now what if we make the tree balanced? Then suddenly the depth shrinks from k to log k. So we should be able to prove that the price of explainability is log k. So what we need is just to make the tree balanced. So we don't want it to be like lopsided to the left or to the right. Okay. And what this thing says is that if theta is very lopsided, which means that f of theta is very close to 0 or very close to m, then we get an improved bound on the gradient. So that's why we can use this to improve our bound. And so let's see. So let's continue. So we still have the same bound, except that the last line is changed using this improved statement. So now we know that for each level of the tree, the total reassignment cost is upper bounded by the L infinity K median cost of one of the children of the node. And it's always the smaller children, like the children with a smaller L infinity K median cost because of the minimum. So now we can build a tree level by level. So every node of the tree has two children, one black and one red, and the red node is the one that is responsible for the total reassignment cost. So now, after we build the tree, we sum up over all of the red nodes to get a bound on the total reassignment cost. And the key observation is that if we look at every root to leaf path, then the L infinity K median cost at every red node reduces by at least half. So the reason is simply that the red node is the child with the smaller L infinity K median cost, which means that its own L infinity K median cost is at most 1/2 times the L infinity K median cost of its parent. So that's why on every path, the L infinity K median cost at every red node reduces by at least 1/2. So since this kind of exponential reduction, exponential decrease in the L infinity K median cost, then if you only look at the red points, then the depth, then there are some tricks you can use to ensure that the depth of the red nodes in the tree is upper bounded by log k. So in other words, the effective depth of the tree is order log k. And then we can show an upper bound for order log k for the price of explainability. And more precisely, the upper bound is order log k log k, because it's not exactly less than or equal, but it's less than, approximately less than or equal. But there's some technical details that I'm hiding. Yeah. Okay. So this gives an improved bound for L infinity k median, and it's nearly an exponential improvement over the previous bound of order k. Okay, so and all these are essentially ideas from previous papers. And now I'm going to tell you how we can use these ideas to get a bound for k-means, which is the setting we are focusing on. And also, I'm going to focus on 2 dimensions in this talk. And if you remember, the bound we have for 2-dimensional k-means is exactly log k log k. So now the task is essentially to translate all of these analysis to k-means. And if we can translate this without losing anything in the Price explainability, then we succeed. Okay. So that's the plan. So let's try to do this also for k-means. So again, we just do essentially the same thing. We take each point and we build a function for that point. But now since now it's k-means, so the cost, the contribution of a point to the k-means cost is Lx squared. So this is the only change. And now previously the gradient is lower bounded by 1, but now since everything is multiplied by Lx, so now the gradient is lower bounded by Lx. And now we can also do the same thing. We sum up over all the points. We build a sum, and for this function, we also know that we also have a lower bound on its gradient, which is just the sum of Lx over all the reassigned points. So essentially, we're just mimicking what we just did for k-median. And we also have some bound, which we also can show that some quantity is upper bounded by the minimum of f of theta and m minus f of theta. So again, mimicking what we did for k-median. So now if we compare what we have here for k-means to what we had before for k-median, so essentially we have so the last 3 lines of the inequality, so we have the last 3 lines of the inequality, but the first line is missing. So what's missing here is that we want to bound the reassignment cost of a point x by a constant times Lx times the diameter. So if we could do this, then we could add a first line to the inequality for k-means, which says that the total reassignment cost is upper bounded by this sum, and then everything is good. So, okay. So next, I'm going to tell you how to bound the reassignment cost of a point x by this strange quantity Lx times the diameter. And also remember that we are now working with k-means, so the reassignment cost is the difference in the squared distances, the new squared distance minus the old squared distance. So that makes the problem more challenging. Okay, so now what we need to show is that the reassignment cost of a point x is upper bounded by Lx times the diameter. So the diameter is W in the picture. So here is the example. So we have a data point x. It was initially assigned to a centroid A, and it's in L infinity distance to A is Lx. So this is basic setup. And suppose we make a vertical cut at theta, and that separates x from A, and so we need to do a reassignment from x to B. And suppose the distance from x to B is Rx. So now now our goal is to show that the reassignment cost of x is upper bounded by Lx times W, which is the diameter. And of course, the reassignment cost is always upper bounded by Rx squared. So this is k-means, so we take the square. So we just need to show that Rx squared is upper bounded by a constant times Lx times W. But this is not true because Rx can be as large as W, and so Rx squared can be as large as W squared. So this is not true, and Lx can be much smaller than W. So this is why k-means is challenging in this with this analysis. So to solve this problem, what we do is a very simple idea. So suppose this goal is violated and Rx is larger than some constant times Lx times W, then we just never try to separate X from A. So we never choose data in this red interval. So we mark this red interval as forbidden if Rx squared is larger than a constant times Lx times W. So now as long as we choose our theta outside the forbidden region, then we achieve our goal. So that's the idea. And now the issue is to bound the size of the forbidden region, because if it's forbidden everywhere, then we are stuck. We need to show that there are still non-forbidden region. And so for that I would like to start with some more basic problem, which is to bound the average distance between centroids. So suppose, like, let's forget about clustering for now. Suppose we have a bunch of centroids in a square of size W by W. And for each centroid I use Ri to denote its distance to its closest neighbor. And again, everything is in 2 dimensions. And also we would like to measure distance in L infinity norm, although that doesn't really matter in 2 dimensions. Okay, so one thing we could show is that the sum of all the Ri squared is upper bounded by a constant times W squared. So essentially this gives us some bound on the average distance between pairs of points. So the proof for this is that we can draw a square around each point with side length R of I. And then the area of this square is proportional to Ri squared. And we can draw these squares in such a way that these squares are disjoint. So their total area is the sum of the area of individual squares. And by upper bounding the total area of these squares, we can upper bound the sum of Ri squares by W squared. So this is a basic volume argument, which shows that essentially the message of this is that if you have a bounded region in 2 dimensions and you put a lot of points in them, then the average distance between these points can't be too large. That's the general idea. And so let's try to apply this idea here. So our goal is to bound the total size of the forbidden region. And let's assume for simplicity that the forbidden regions are disjoint, because if they are not disjoint, then the sizes are even smaller. That's one reason for this assumption, but it also simplifies things a little bit. And based on the ideas, based on the bound on the average distance between centroids that we just saw in the previous slide, we can also use a similar argument, which shows that the sum of Rx squared is upper bounded by a constant times W squared. So just similar volume argument, although you do need to modify the argument slightly. And yeah, but basically this is the bound. And what this shows is that if you sum up over Lx over the forbidden region, then by the definition of the forbidden region, Lx is smaller than Rx squared divided by the constant C and the diameter W. And since the sum of Rx squared is upper bounded by W squared, by choosing a constant C large enough, we can bound the sum of Lx by W over 2. So this means that from 0 to W, the total width of forbidden region is at most W over 2, which means that the total width of non-forbidden region is at least W over 2. So this means that we do have a sufficiently large non-forbidden region. Okay, so essentially this completes the story. So having our non-forbidden region is sufficiently large for us to implement all of the analysis I just mentioned, and essentially that's the main story of our technique. And I guess I would say that the main technical contribution of our work is this forbidden region idea. And now I would like to I would like to mention a few things about which I cheated in the talk. So first is the challenge of follow-up reassignments. So this means that a data point can get reassigned multiple times. So for example, in the first round, it gets cut from its current centroid, so there's a reassignment. And then later, in the next recursion, it also gets cut from its current centroid and it gets reassigned. So a single data point can be reassigned multiple times, and this can cause a problem. So essentially, in the k-median setting, we showed that the reassignment cost of a point is upper bounded by the diameter. That's what we used. And in the k-mean setting, we showed that the reassignment cost of a point x is upper bounded by Lx times the diameter. So this relies on the forbidden region idea. So outside the forbidden region, this is true. But what we really need in our analysis is actually is a bound on the total cost of all reassignments of a point. So because we need to take this into account, right? We need to, since a point can be reassigned multiple times. So what we really need is the total cost of all reassignments. But this is no longer true for k-means. So it's true for k-median because diameter is such a large quantity that it bounds everything. Like no matter how many times you reassign a point, you can't pay larger than the diameter because the diameter only shrinks after you go from a problem to a subproblem. But now our bounding k-means, it relies on this forbidden region business, and now it's no longer true that the total cost of all reassignment of points is upper bounded by this. So this raises a challenge, and in our paper we use there are techniques in our paper that is specifically used to deal with this case, but I don't have time to talk about it in this talk. And also, of course, our paper is not just about the 2 dimensions. So we also had results in higher dimensions, and there are also challenges in higher dimensions. Specifically, the volume argument I just mentioned only works for 2 dimensions in its exact form. So in D dimensions, we also have some volume argument, but it's much weaker than the bound in 2 dimensions. And the biggest trouble is that this bound in D dimensions is not compatible with the analysis, right? Because in our analysis, we really want to bound the reassignment cost by Lx times W. So that's essentially, like, in some sense, only designed for 2 dimensions, for the 2-dimensional volume argument. And but in our paper, we had techniques that also that handles higher dimensions. Okay, so I think that mostly concludes the talk, and I have some final remarks. So first, there's this open question, which is to achieve constant upper bound on the price of explainability for k-means in 2 dimensions. I think we also discussed this when I was answering a previous question from the audience, and so I think this is still open, and the current upper bound we have is log k log k, but I believe that it's plausible that this can be improved to a constant. And after our work, people also considered many interesting variants of explainable clustering, and again, this is a rather new notion and a young field, so there are a lot of questions that we want to answer, and there are a lot of exciting new directions in this area. So people, for example, people consider the bi-criteria setting, where we allow the decision tree to have slightly more than k leaves. So this turned out to be very powerful. It reduces the price of explainability for k-means from k down to roughly log squared k by having slightly more than k leaves. And Li and Shine is going to talk about this in this workshop tomorrow. And people also consider the problem where we only require explainability for most, but not all points. So in other words, we allow some outliers for explainability. And people also consider the setting with shallow decision trees. And I guess the idea here is that the shallower the tree is, the more explainable the clustering is. So that's why people also want to optimize the depth of the decision tree. Yeah, I think that's all for my talk, and I'm happy to answer your questions.